Okay, welcome everyone. Welcome to the vector tutorial session. Basically, we're going to be going over, using vectors in game development, and then kind of going over the basic vector operations, and then kind of finding out what it does and when to use it and stuff like that. So, vector, right? In the math sense, right? You kind of just learned it as, so if you have a vector v, kind of just as ordered collection of numbers, right? So you would have entry v1, v2, all the way to vn, and this would just be an n-dimensional vector, right? In game development, we usually only work in two-dimensional or three-dimensional vectors, right? So you would have a vector v1, v2, and then three-dimensional vector would be 3 entries. But we like to kind of interpret it as, instead of just entry 1 and entry 2, kind of like to look at it as the x component, this didn't work, right? X component and the y component. And right, for 3D vectors, it would be like x component, y component, and of course there's a z component now. Right? And then these can represent things such as position, right? Position, where it is in the x position, y position, z position, and then velocity, what's his speed in the x direction, stuff like that. And as well as acceleration and other things like direction, heading. Sometimes, very rarely, we have 4-dimensional vectors, right? And it's not used to represent 4-dimensional space. It's more so it can be multiplied by a special matrix that can all do linear transformation and displacement all at once. So you would see it something like Vx. It's not working. All right, let's do another one. So Vx, right? Vy, and then Vz, right? And then the 4th entry would be a special number, usually 0 or 1, right? And what would end up happening here is that you would multiply this by, let's say we want to rotate an object as well as displace it, right? So you would have it, so you would multiply it by some block matrix that has a rotation matrix, and then a displacement matrix, and then a 0 matrix, and then a 1 matrix. So if I put it all together, right, Vx, Vy, Vz, and then 1, right, these 3 entries would be transformed by the rotation matrix, right, and then the 1 would act on the displacement matrix, and then it would shift over. Not very important, I just want to mention that, because Unity has a matrix 4x4. So if you're wondering why there's a 4x4 matrix, that's exactly what's for. All right, so use cases for just vectors itself, right? You can represent things in space. So let's say there's a player here, right? Somewhere, right, in the game world, there's an origin, right? Let's say it's here, right? Let's say there's a screen, and let's say the origin's right there. So you would have a vector going from where the origin is to where the player is, right? And then you can also represent velocity with it, right? The speed in a certain direction. In this case, it's moving in this direction. And you would also have acceleration, right? The rate of change of the velocity, right? So as time goes on, this velocity will, go towards more like that. So that leads to our first checkpoint is we just want to try changing the position of some objects in code. So let's go to Unity, right? Let's do this. Nice. Okay. So if you go to Unity and open it up, you might get something like this, right? Is that what you see? Kind of. Let me full screen this. Is that kind of what you see? So do you have Unity Hub? Okay, so Unity Hub. And then, do you have it kind of in this list here or no? Okay, so you have to clone it, and then is it in like a?
You have to update the version on your hub so that you can actually open it, because the version that you posted is like a bit obscure. So you just have to, when you install it, program.
Do you have the 2021.3.6 F1 or version?
I'm like
older is fine.
But I have like 0.3, like 14 or something.
Oh yeah, that's fine. That's fine.
But like you can press like the ...
Yeah.
Just change the version. So
All right, so let's see what you got here. Right, so you want to click open, and then go to wherever you downloaded it. If it's not extracted yet, you're going to have to extract it first. Yeah, so just do that. Okay. All right, so whoops, you might see something like this, right? So there's two folders here in the assets window. The only one I want you to focus on is the scenes folder and the exercise scripts folder. So first of all, let's go to scenes and then click on C1 vector position scene, right? And this is what you should get. I like to split the game in the window, the scene window up. So I'm gonna do that. My method of drawing like grids uses something called like gizmos, right? To turn that on, you have to go up here in the top right and then click on gizmos. So if I click that, you'll kind of get this. It's kind of hard to see the grid on the thing, but whatever. So yeah, you have to click on that to turn that on. And then, right, to actually start writing code, right, that's going to be in the exercise scripts folder, and then we're going to click on C1 vector position.cs, right? Hopefully you'll kind of see the pattern. The next one, you're going to click on C2. All right, so that's open. Is it open for everyone or most people? Okay. You might have to like drag up. Oh yeah, so you're in the scene window, you have to click on game. Yeah, and then click this one. All right. So, is it okay if I explain the task here? You're just gonna be moving objects to like certain position, right? So, if you look in the scene here, right? There's a square object, a circle object, and a hexagon object, right? And what I want you to do is, right, I want you to move it to a specific position that I specified in the C# file, right? I want you to move the square to, position 2.1, circle to -4.3, and then hexagon to 8.5 and -7.5. So I'll give one example, like for the square, right? We want to change the position of the square. And what that means is, if I click on square here and look in the inspector, right? Position is inside this component called transform, right? And this transform component is held by this square object, right? So what we want to do is access the transform, and then within the transform, access the position. So it looks something like this. So we have access to square here. So we type square, and then to access its transform, write transform. And then to access the position of that transform, we type position, right? And then we just want to assign some value to it, right? But how do we make a new 2D vector, right? Well, we type new vector 2, right? And then we pass in arguments. In this case, we pass in 2 arguments. The first is for the x component, and the second is for the y component. So if I want to move it to position 2.1, right, we just type 2f 1f. And I'm putting f just to explicitly say that, okay, that's a floating point number. And that's important because if I do 1.0, right, it's going to say, cannot convert from double to float. And that's going to mess you up for when you do the hexagon, so make sure you put the f there. All right, so I'm going to give you 2 minutes to move the circle and the hexagon. I guess I should run it first to see if it actually works, right? Once you write the code, you should go back, and then if you click play, you should see one of the objects move over, right? In this case, I think it worked, right? It moved to 2, and then 1 upwards. So that's how you can check. You also have the position up here, so you can just check with the text and what's written in the file. All right, so I'll give you 2 minutes. All right, okay, so I'm just gonna go over the solution right now because it's 4:53. So it is mostly just copy and paste, right? If I want to move the circle to, you know, whatever that position is, right? Instead of changing the position of the square, I just, change the position of the circle, right? And then I would assign, vector 2 of, -4 and 3. And then for hexagon, I would just access the transform position of hexagon and then put in 8.5 and -7.5. So if I go back,
The thoughts were pretty hard to read.
I'm sorry. Do you have it working though?
No errors so far.
Okay. Wait, no errors?
Yeah, no errors.
Okay, good. So yeah,
No red lights.
you should have this, right? That's basically the solution. Should be pretty simple, right? Once again, I'll emphasize if you do that, you're gonna get an error, right? Because this 8.5 is a long type, right? Which is more precise than float. So it can't put everything inside a smaller, less precise data type. So you gotta put the F there. All right. Okay. So let's go on to vector addition. I think I might have been recording the camera there. Let's see. Okay, I may have been. That's the solution, in case it wasn't recording the screen. All right, here we go. Let's go back. So vector addition should be. What's it not doing? Okay. So it should be pretty familiar to most of you, right? U plus V. How is this defined? Well, if you have entries of right, if you have UX, UY for the entries of U, and then VX, VY for the entries of V, it's just the summation of these entries, right? So what does that look like, in terms of like arrows and like graphs and stuff like that, right? So if we have a graph, let's say that's like 2, right? There's a vector going up to there, let's say that's U. And if we have a vector, let's say go up to there, and that's V, right? And the vector addition is something like up there. And how did I get that, right? I basically, just like move this vector, right? If we're doing U plus V, I basically just, right, from U, I want to add V onto U. So I just take this vector and like put it like that, right? And if we were to do V plus U, right? I'll be adding U to V, so I would just be putting this U vector kind of like that, right? And then this, if this is equal to W, then this, right, this vector here is going to equal to W. So some use cases, right? Let's say I want to move an object. Let's say, once again, I have this thing, and the origin's here, my player is here, right? That's its position vector. I want it to move, let's say 2 units in some direction, right? Say I want to move kind of like that. I just need to add the position vector with the movement vector, so it kind of goes up here, right? And then you can apply vector addition to velocity, right? Add acceleration to velocity to change it, add velocity to position to change the position, stuff like that. Other use cases, let's say when you're calculating, there's this notion of net force, right? That is, let's say you have some object, right? And you can think like there's different forces acting on this object, like one of them would be like gravity. So actually here, right? And then there could be another force, right? Such as, I don't know, wind, right? And then maybe like I'm deliberately pushing that object kind of downwards in this direction, right? Applied force, right? If we were to sum these vectors up, it would, it would kind of, you could kind of see it as one force acting on this object. So like, to give an example, right? Let's say I take my phone, right? And then kind of like hold it up against this wall, right? There's multiple forces acting on this, but the phone is not moving. So it kind of seems like there's no force acting on it, if that makes sense. So all the force is acting on it, so like gravity is acting on it, this wall is acting on this phone in this direction, I'm applying a force that way, and then there's also friction going down or upwards depending on how hard I push on it, right? That is all adding up to 0, right? So yeah, so for calculating net force, that's important. So that leads us to our second checkpoint, all right? For the second checkpoint, we're just gonna have it so when we press the button, we kind of move in certain directions. So what you're gonna do is open up C2 script, right? And you're also gonna open the C2 scene. Okay? So once you're there, right? The goal here, the task here is to, right, when you press up, I want you to move the circle upwards by 1 unit. If you press downwards, move it down by 1 unit. Press right, right in 1 unit. I think it's self-explanatory. And then space key, right, when you press space, I want you to move the circle back to the origin. So, right, to give one example, right? Also, yeah, I want you to, instead of acting directly on the transform position, I want you to act on this variable, this local variable I said here. So to add a vector, right, you can kind of see it in 2 ways, right? You can see it as adding some vector to position, right? So let's say if I want to move the circle up 1 unit, right, I want to add a 2D vector that goes up 1 unit, right? Or you could see it as assigning some addition of 2 vectors, right? I want to add these 2 vectors and then assign it to position. So I think that's all the info you need to do this. So just fill in down arrow, right arrow, left arrow, and then space. And in the end, if you press the button, you should see it move like that. Did I save? I don't think I saved. Yeah, there you go. You gotta save first. All right. So if I press up, right, it should go up by 1 unit. All right. I'll give 2 minutes again for this one, or 3. Yeah, I forgot to mention. Okay, I forgot to mention. So your thing might look like this, right? It might look like, I don't know, it might look something like that, right? To kind of avoid that problem, just put it to 16 by 9. So like even if you scale it, right, it kind of looks nice. All right, I'm gonna go over the solution now, right? It is, again, just kind of just copy and paste, right? Instead of going upwards 1 unit, I go downwards 1 unit. I'll do this one differently, right? Position plus equals, right? Vector 2 has a static method, static property, where you can kind of just get the left vector or the right vector. So if I just write vector 2.right, this automatically gives me a vector, right? It's a shorthand for writing vector 2, 1, 0, right? That just immediately just gives me 1, 0. So that's very convenient. There's a up, there's down, and there's forward. No, there's no forward. That's for 3D. In this case, right, I would want to put left. And even for a 0 vector, right, I want you to put the position back to 0, right? So we want to assign a 0 vector to it, and we just do that by writing vector 2 dot 0. that make sense? All right. All right, 20 minutes in. Okay. Let's go. Do people want to copy that code or?
Alright,
Well, let me clean this for you. So, vector difference, right? I'm kind of cheating because I need to introduce scalar multiplication first, but whatever. U minus V, right? What does this mean? Basically just taking whatever component of, V is and then just subtracting the U components, right? If you look at it visually, let's say I have a vector here, let's say that's U, and then vector V, right? What performing this operation would get is a vector that goes from U, right? From V to U. So it would be a vector that kind of goes like this, right? This here would be U minus V. But you have to remember that it goes from V to U, not U to V. So, right? It's kind of confusing, right? If you haven't worked with it too much, but you can kind of verify it, right? If you look at U, this is just a vector addition of V and U minus V, right? Or whatever the vector difference is. So under that assumption, right, we should expect V plus U minus V to hold, right? V minus V cancels out, so we get U and U. If we assume the other way, right, V minus U, what will end up happening is it will simplify to U equals V. And right, that's a contradiction because right, I drew V and U to be different. So yeah, if you want to check, that's how you can check it. Another way of seeing this is it's basically just like whatever this difference is, right? It just holds U minus V. What it actually holds is just the delta difference, right? So if I subtract U from V, well, U is a greater number, so I expect this component to be bigger. Okay? Hopefully that makes sense. Vector difference is very powerful because it allows you to get the direction of something. So if I have, some, let's say, I don't know, it's a circle, it can be like a player or something, right? And then you want to get the direction of from the ball to the mouse, right? We just subtract whatever the mouse position is with the ball position, right? And right, it's good for when you want to like shoot in a certain direction, right? In games, stuff like that. It's also good for later on when we do checkpoint 3, accelerating towards some position, right? It starts kind of charging in that direction. Yeah, very powerful. The thing is, it's not as powerful without vector normalization, so we're gonna have to get to that. But first, we gotta talk about scalar multiplication. So let's talk about that. And then I'm gonna do an example with time, not delta time. All right. Scalar multiplication, right? You have CV, where C is just a number, right? It's a scalar, and it just basically whatever multiplies whatever that magnitude is by a factor of C. So if you have a vector, it's like V, and let's say I multiply it by 2, right? This length is just going to double, right? So now this is 2V, and then if I do 3V, this would be like something like here, right? What happens if I multiply it by a negative number? Now it kind of just goes in the opposite direction. It keeps the same magnitude, but it just goes in the opposite direction. And then, right, same if you do negative 2, it just doubles the length in the opposite direction. So, what is this good for, right? Once again, not as useful just by itself, but there's one case that's really useful. So let's look into that. There we go. So we're gonna modify this code, right? And right, like you mentioned, right, how do we make it so instead of, right, like how do we make it so when you hold down the button, it kind of just keeps moving in that direction? Well, there's another method called get key, right? There's also get key up. That's when when you let go of the button, right, that would activate. Get key down happens when you, on the first frame that you press the button, and then get key always returns true when you have it held down, right? So let's say that's our first approach to, making it go up, right? And we would want it so it goes up, right? In 1 second, it moves up 1 unit. So that's kind of our goal here. So let this kind of be our first approach. It's not going to work, as some people might kind of, guess. So if I hold down the button, it's going to kind of, oh, wait, what is it doing? All right, it's not moving. Let's see. I think I got rid of this thing. Yeah. All right, so if I hold it down, what do I do? Get key. All right, let's do this. So if I hold it down, it should kind of zoom off into space, right? And that kind of makes sense, right? Every frame that we're holding down this button, we're moving it up by 1 unit. And it's updating super fast, right? How fast are we updating this, right? If we look at stats here, we're updating it at 380 frames per second, around that much, right? So, and this can vary, right? Right, it's not consistently 380 FPS. It's around 380 FPS, and even on slower computers, right, which I can kind of simulate by taking off the charger, unplugging the charger. Now I'm getting 30 FPS, right? So on some computers, it's gonna run slower. So we can mitigate this by multiplying this by however long it took to get to the next frame, right? So I want to move up 1 unit, but I want to kind of shorten this one vector by however long it took. So if I were to do this and then now play it out, you should see that every second it should move up 1 unit. So 1, 2, 3, 4. Does that kind of make sense? Okay. I was gonna give more examples, but I guess it just makes sense. I don't know. All right. So yeah, use of scalar multiplication right there. All right. Let's go back to cam mode. I have so many markers. I don't know which one works. All right, magnitude. So finding the length of a vector, right? Let's say we have a vector v and we want to find its magnitude. Then it's just going to be the square root of all the entries, right? The square of the entries, the sum of the square of the entries, right? And then squaring all that. And you can kind of see that this is basically just a Pythagorean theorem, right? And that's kind of all it is. Right? If we draw a vector to find this length, right, we just use Pythagoras to find this length right here. Use cases for it, right? Let's say it's good for making kind of radial trigger zones, right? So like, let's say you have a turret here, and then it has kind of a zone, a circular zone with a radius of like, I don't know, sure, just make it radius, right? And we only want to activate, right? Let's say there's a player here, and it only wants to shoot at the player when like the player is within this zone. So we can get the vector difference, right? The player's position minus the turret position, and then we compare it. Let this vector be the d for difference, right? If the magnitude of that difference is less than radius, then like, I don't know, shoot at the player, right? Magnitude is also good for vector normalization. So I'm going to get into that right now. All right. So vector normalization. So let's say we have some vector, right? And we want it to be of length 1, right? We don't care about the length at all. We just want its direction. Well, let's say you have a vector u, and we want to kind of turn this into a unit vector. What we do is we take the vector, and then we divide it by whatever the length is. Hopefully that kind of makes sense. What is this good for, right? It's good for when, it's very powerful when you mix it with scalar multiplication. So like, let's say you have some direction, right? Once again, I'll just use I don't know, some like bad enemy thing, and it's like trying to shoot at the enemy, trying to shoot at the player. We can get the vector difference, right? We have the direction, but we don't kind of like the speed, right? Because depending on how close they are, it's going to like shoot faster or slower, right? So what we want to be able to do is kind of control how long this vector is. So what we can do is first normalize it to be a unit vector, and then scale it up to be whatever we want it to, right? We can do that for anything, right? Right. If I want it to be like within this zone, I just normalize it and then scale it up. So it's very powerful. It's like if you don't like the length of something, just normalize and then scale it up, right? So that leads us into the third checkpoint. But I think I'm gonna have to give some example first. Let's see. 520. All right. So, oh yeah, not C3. I'm gonna give an example. So I'm gonna play this scene here, and then we're gonna get two types of motion, right? The blue ball right here is moving at constant speed, right? And the red ball here is accelerating at with a magnitude of a constant magnitude of acceleration. So, do people know like speed, velocity, and acceleration? Okay, so would you kind of have an idea of how to implement that red ball behavior then? So basically what's happening, okay, let's kind of break it down. We have this thing here, and all this is doing is, right, in, whatever direction it's, it's wants to go towards, it's moving at a fixed speed, right? I think it is 5 units per second, so let's check, right? 1, 2, right? It ends up there, so it's like 5 units away. So it's 5 units per second. All it's doing is it's getting the difference vector, right, from the ball to my mouse position, and then it's normalizing it and then it's multiplying it by 5, right? That's how we get this effect. And I believe I have the script here, physics velocity, right? If we look at the code here, right, I am subtracting it, and then I'm normalizing that, difference, and then I'm multiplying it by speed, which I defined to be 5 up here, right? And then I'm using time dot delta time to add velocity to whatever the position of the circle is. You can kind of apply the same idea to acceleration, right? In this case, right, we're not adding onto velocity. We're not adding onto position. We're adding onto velocity. So, right here, if you kind of break it down into components, right? Like right now, the x component is positive, but sorry, this should be the other way, right? Now it's negative, right? And it's because the acceleration is like constantly changing x to be, go positive, and now it's going go negative, right? So it's the same idea of applying velocity to position, except now you're applying acceleration to velocity. So now, would you kind of know how to implement the red ball movement?
Can you go back to the go?
Yeah, like this thing. So it is kind of the same logic. And right, I should remove this. This is not the actual script. the actual script is in, it's gonna be in, right, checkpoint 3. Right, and also the scene is also gonna be in C3, right? Currently, this is what you have. It does nothing. But I need you to make this ball move, ball accelerate towards the mouse position at 5 units per second squared. And the variables you have, right? You have the mouse position, you have the circle position, you have the magnitude of the acceleration, and then you also have the velocity, right? And then I just need you to set the acceleration to be, you know, the right amount. And then, right, add acceleration to velocity, and then add velocity to position. Should I bring up the other code again? I can like dock it. Can I do this? So if it helps, try doing the velocity thing first. Try making the ball move with a constant speed.
What's the dot normalize method?
So right. I should have kind of explained it. Okay, so what did we go over? Vector difference, right? We can subtract two vectors, right, with the minus symbol, right? Right, we just subtracted two vectors from one another. Getting the magnitude, right? What we can do is, if we have a vector, we can just call magnitude on it, right? And that would get the magnitude of the vector. For normalize, normalizing a vector, right? We can call mouse position dot normalized, and what that does is it returns a normalized version of mouse position. So right, and then now we can assign it to some. We can assign it to some other 2D vector.
And what does normalize mean?
So like normalize is the vector normalization I showed you, right? Returns this vector with a magnitude of 1. So it maintains the direction, right?
Like it's the unit vector.
Yeah, it's the unit vector. So it maintains the direction of that vector, but it just makes the length 1. So, should I kind of just like go through this problem? Okay. So,
Isn't this frame rate dependent? Like how fast it accelerates?
so that's why I'm using time dot delta time, right? So velocity we can represent as 5 units per second, but we only want to take like a little bit of that vector and then move it by a little, you know, move the position by a little bit. So we have, let's say 5 units per second, right? It's a vector that is like this long, right? Right, this long. But when we actually move it, we only want to move by like this much. And that's what we're doing, right? Delta time, this is in seconds, by the way. So like, maybe like around like 0.01, right?
Okay, cool.
So like, move by a little, move by a little. Right.
That's a nice question. Field? Variable?
The delta time?
Delta time is a field, right?
It's, I think it's called a property in C#. Well, it's like
No, like what is it?
So delta time?
Yeah.
It's the interval. It's the interval in seconds from the last frame to the current one. So however long it took to kind of update the next frame, right?
Oh, so it keeps updating itself so that it ensures that there will be 1 second.
So let's say it takes, right, I'm running the game at 1 frame per second. That would be 1, right? It would hold a value of 1 because it took 1 second to update that. If it was 2 frames per second,
It would be half.
yeah, it would be 0.5. And then, 4 frames per second, it would be 0.25. All right. All right, so I'll kind of go over the acceleration problem. This. That. All right. So we have a ball, and right, its position is right here. And let's say it's moving in this direction, right? That's the velocity. This is the position vector. And then now we also have acceleration, right? Let's say the mouse is there, right? It wants to kind of, rush, kind of charge towards the mouse. So, acceleration. So, kind of, high level thinking, right? What acceleration is doing is it's just adding to velocity, right? If it's accelerating in this direction, right, every frame it's gonna kind of look like the velocity is like changing like that. Does that kind of make sense, right? And then with this velocity, right, I want to make the position kind of, since velocity is kind of like going like this way, it might look like it's gonna go kind of like that. Does that kind of make sense? Or is that kind of weird? Right now, now it's getting messy. This was the initial velocity. It's going upwards, right? If it stayed that way, it would keep going up like that. But it's changing, and the acceleration is pointing kind of downwards. So you would expect velocity to kind of, let's think about it in terms of components, right? Velocity has a positive y component, right? If you can see it like that, right? Since acceleration has a negative y component, it's going to eventually make it so speed is no longer, right, or the velocity is no longer pointing up. It's now going to point downwards. So it's going to get that, you're going to get that motion. So basically, you're basically adding acceleration onto velocity, and then velocity is adding onto position. And the way you would get this acceleration vector is, once again, right, find the vector difference, and then normalizing it, and then scaling it up to be whatever that magnitude is. Is this a little too confusing? Maybe it'll just make more sense if I kind of just do this one. Yeah, I was thinking like it's kind of conceptually weird, but it's more like understanding the concept of acceleration and velocity rather than like doing the actual code. So I'm gonna keep this here as well, just to see the similarity. So at a high level, right, we have acceleration, and that's going to be equal to some value. And then what's going to end up happening is we're going to add acceleration to velocity, and then we're going to add velocity to the position, right? But we have to multiply it by delta time, right? Because we don't want it to go like 5 units in one frame. We want it to go there in 1 second. So we use time.delta time to make this whole thing, this whole vector, right? After 1 second, it should add 5 units in that direction. And we would do the same for adding onto velocity, right? But what do we assign to acceleration? Like I showed there, right? I want to get the vector difference, right? I want to get the direction towards the mouse position first, right? So I just do mouse position minus circle position, right? That's the vector difference, but we don't like that length, right? That length can vary depending on how close the mouse position is to wherever the circle is. So what we do is we first normalize it, and then we multiply it whatever the magnitude of the acceleration is. Hopefully that made sense. Does that make more sense? Acceleration, there you go. So yeah, and then let's compare it with the velocity one, right? It's basically the same, right? Acceleration equals, mouse position minus circle position, and then it normalizes it. Instead of multiplying by the magnitude of the acceleration, we multiply it by the speed for the velocity version. And then, right, it's the same thing, acceleration, adding acceleration to velocity, adding velocity to circle. In this case, we're adding velocity to circle, and that's kind of it.
You have to multiply it by delta times twice, or only you're multiplying acceleration by delta times over here, so only do it for.
So, yeah, okay, so this is what would happen. So you're thinking, like, am I allowed to do this, right?
Yeah, because on the other
then the velocity is going to grow really, really fast, right? It grows that much faster. It's going to grow faster when the frame, frame rate is bigger, right? If I do, let's say,
yeah, I got rid of delta time and the ball just became
so
slinky.
yeah. So if I make my computer slower, now it's not doing it as much, but right, there's that problem of now it's frame dependent, right? So if I put the charger back in, now it's going to go faster because update is running faster. So yeah, we don't want velocity to increase that fast. So we want to do acceleration, right? That's the change in velocity per second, right? And then we want to only increment it by a little bit by multiplying it by this delta time. One way to think about it is, okay, what if this was 1, right? We should expect that, after 1 frame, or let's say you're running the program at 1 FPS, right? So every frame it's updating once. So time.delta time is going to be 1, and you should expect velocity to have increased by whatever acceleration is. Hopefully that makes sense. Okay. Should I talk more about this, or should I just go into dot product? What is that?
You can go.
Oh, okay. All right. Okay, let's change this back. I think the camera moved, so there you go. All right. So now we're kind of getting into the territory. Like you learned about dot products, right, in Math 111, right? But I think after I'd taken that course, I still didn't really know like how to see it visually. So, okay, good. Dot product, right? U dot V. Right, the definition of dot product is just take sum up the product of the entries, right? So let's say ux, uy, no, ux, vx, and then uy, vy plus in 3 dimension, right? You would have uz, vz, right? But this kind of doesn't make much sense, right? It's like, what's that supposed to mean? Another equivalent statement is multiply, right? Find the product of the magnitude of whatever the vector u is, whatever the product of whatever the magnitude of v is, and then multiply that by cosine theta. And theta is the angle between those 2 vectors. It still doesn't make much sense, but right, it's better than this. So let's kind of break this down. One thing you might have learned is that u and v are perpendicular or orthogonal when the dot product is 0, right? So they're perpendicular when u dot v equals 0, right? This would also be the case when it's kind of like this, right? Or something like that, right? Let's kind of call this, let's call this case 1, right? And there's 2 other cases. That's when dot product is 0. orthogonal, right? What happens, right? When is it that the dot product is greater than 0, right? That'll be when kind of the vectors are kind of facing relatively in the same direction, right? And we would say that the dot product is greater than 0 when the angle is acute, right? Less than 90 degrees. And this dot product gets bigger the more similar, right, the direction it looks towards. So like the dot product of this, assuming the same direction, or no, the same magnitude, right? The dot product of this would be greater than the dot product of this. But mostly just focus on the cases here, right? The case, this would be case 2. And then you would think like, okay, well, case 3, it's probably the case that, dot product is negative, right? And this would happen when they're kind of facing away from each other. And you can also see it as, okay, well, the angle made by them is acute, right? It's kind of like greater than this orthogonal line. So yeah, dot product is 0 when it's orthogonal. Dot product is, greater than 0 when it's kind of like looking kind of the same direction. And then dot product is negative when it's kind of looking the other way. You're kind of like negatively looking in the same direction.
Like if they're obtuse.
Yeah, you can see it that way. You can see it as well, okay, well, dot product is comparing how closely those vectors are looking at each other or looking in the same direction. So use cases, right? We can kind of let's say you implement, I don't know, kind of like backstabbing, like in Counter-Strike or something, right? You have a player here, you have a player here, right? This player, let's say P1, and then player 2, right? Player 1 is, well, P2 is kind of facing this way, and he's also facing this way, right? But P1 is relatively like behind, right? So we would say we can only, P1 can, the player 1 can only backstab the second player if he's behind the player, if he is behind, player 2. So we would kind of say, okay, take this vector, right, this difference vector, and whatever direction P1 is facing, right, and if that dot product, the direction that's facing, right, if this is negative, then we can do like a backstab. Sorry, this should be 0, right? Only if the dot product is negative can we perform a backstab or something like that. That's one use case. Another one is, if you kind of look at this, right? If we assume that u and v, those two vectors are kind of unit length, right? Then this would equal to 1, and this would equal to 1. Then the dot product is just equal to the cosine, right? So we can kind of have it, so let's say kind of like a stealth game, right? Let's say there's a guard here, and it kind of has, some zone that, it can detect the player, right? We can have it so, okay, well, let's say the player's over here, right? And then this is kind of like where the enemy is looking down. Let's say this is U, and this is V, right? We can say that the enemy can see the player if the dot product of, U being that, from the enemy, and let's say that's the enemy and that's the player, right? From the enemy to the player, right? If that vector and the dot product of, where the enemy is looking towards is greater than some constant, right? Like let's say 0.9, and 0.9 is equal to cosine theta, right? If they're within kind of that zone there, then we can detect the player, and I don't know, it needs to like chase him or something like that. So let's kind of do that, right? So one of the things, should have brought this up earlier. Let's switch this back. So, what's it called? Press F to pay respects, right? You know, it's a famous meme. And, right, we can kind of make this using dot product. Like, what I mean is okay, well, if the player is looking at this F symbol, right, we want this, you know, text pop-up, you know, come up on the screen, right? Only if it's looking towards it. And we can implement this using dot product, as in, okay, is he looking near it or is he looking away from it, right? That's dot product stuff. Yeah, I'm sorry. Let's do something like open image, new tab, right? It's kind of like this. So imagine if instead of looking at F, it's like looking over here, right? Looking over there, right? This pop-up should not appear. It should go away. But when it looks towards, when it is looking towards F, right? This thing should pop up. So that's kind of the checkpoint for it. So let's go to C4, right? We get this, and then go to C4 dot product, right? When you play, you should be able to see kind of this F here, right? But you want some, you know, text to pop up when you're looking at it, and also you only want it to pop up when you're within a certain zone, which is kind of like this circle shown right here, right? So, how do you compute the dot product in C#, right? In Unity has this class, right? In the vector2 class, right? It has a method called dot, and it takes in two vectors, right? Left-hand side and right-hand side. So let's say, I don't know, right? I have the camera direction, right? The direction of, you know, wherever the camera is facing. And then we also have the vector difference from the camera to that text that I write, the F, right? If I were to, you know, put those two vectors in, then I would get the dot product of those two vectors. So using the idea of dot product, you think you would be able to kind of do this? So, right, I need to go over the task, right? I only want you to do it. I only want, right, so I want you to set can pay respect, right? And that boolean is right here. And what this is gonna do is, if it is active, right? If it is active, it's gonna activate some text, right? That line is there. So if can pay respect is true, then it activates some text. Otherwise, it sets it to false.
Should it be a vector 3 so that if you're facing?
Oh yeah. Yeah, it should be a vector 3. Yeah. So in this case, right, we're in 3D space now. I didn't go over 3D, but you know, just using that idea of dot product, I feel like you should be able to do this, right? And I only want you to trigger it only if, right, the angle is less than 15 degrees apart. And I kind of gave you a hint here. Cosine 15 is going to equal to 0.966. So to kind of give you a hint, right? You're going to have something like, okay, whatever the camera direction is, and then whatever the, you know, the vector going from the camera to the F text, right? If the dot product of that is greater than 0.966, right? Then you should make it pop up. So, kind of what we want to do is this, right? Let's kind of get this stuff out of the way. So we have camera. And then it's kind of looking in some direction. And then we also have the text, right? And we only want the text to pop up if it's kind of within this range, right? And we can kind of think of it as, okay, well, there's a vector going from the camera to the text here, right? Only if the angle is this much do we want to kind of activate this text pop-up, right? And I mentioned that, right? If you make two vectors orthogonal, right, and you take the dot product of it, they basically just computes the cosine. So if you know what the cosine is, right? Right. In this case, I think I wanted you to do cosine 15. So 0.966. Right?
You can also just write math.cos 15.
Yeah, you could do that. No, you can't, because you don't know the angle, right? How would you get the angle of?
No, but instead of writing 0.966.
Oh yeah, you could.
Exact value.
You
We're
could.
doing an operation at the time.
What is that?
Oh, right, yeah.
I guess better just have a constant value than when you have to recalculate.
Yeah. So one of the reasons to just use the dot product is to not perform this cosine operation, right? Cosine in programming is kind of expensive, right? It's not really a big deal if you're making small games, but like later on, right? If you're doing like a lot of stuff, you're calculating angle and all that, you might just want to just use the dot product, and the dot product is just bx plus uy by, right? It's just product and addition, right? That's really simple calculation compared to cosine. I don't even know how to calculate that. So I don't know. Does this give a better idea, right? You basically make it so if the dot product is greater than 0.96, right? They're basically aiming right in the same direction. Make the text pop up or set can pay respect to true. And right, emphasizing once again, right? These are unit vectors, so you're gonna have to normalize and then do the dot product again. Would it be better if I kind of just like went over the solution, like just like kind of step by step? Okay, I'll just go over the solution unless people are still figuring that out. So, all right. So like I said, right? I wanted that text pop. I want to set can pay respect to true. Only if that angle is like kind of like, only if that angle is less than 15 degrees, right? And I have here, right, cosine 15 is going to be equal to 0.966. So what I can do is I can just take the dot product of this camera direction, right? It's like the direction that this camera is facing. And then the difference vector, right, that goes from the camera to whatever the text is, right? Cam to F. The thing is, we want to make these all unit vectors, right? Because we want to get cosine directly. We don't want this, weird multiplying by the magnitude of a vector, right? So we normalize this, and then we normalize this. So maybe right, instead of solving it right now, how about we kind of just see, what this outputs. Let's do this. So, right? Let's say I'm looking, right? The F thing is over there. Let's say I'm kind of looking orthogonal to that text there, right? You should expect the dot product is to be kind of near 0, right? I can't get exactly orthogonal, but right now, like, it seems like it's kind of 0. And then if I like look along this kind of axis, it's gonna kind of stay 0, right? Because this is also kind of, I'm still looking in the orthogonal direction, and right, if I look this way, dot product should be near 0 as well. And the closer I look towards this text here, right, the value is going to increase. Also, I should say, right, there's the console output down there. There you go. Right, and then when I'm looking directly at it, the dot product is near 1. And then you might be able to guess, right, if I look directly away, it should be, you know, -1, something like that. So yeah, the closer I look towards F, the greater the number becomes, like the dot product increases, and then if I look away, the dot product is going to decrease. So that's kind of how it works. So we kind of want it, so like, okay, well within, right, I want this, you know, dot product to be greater than certain amount for this text to pop up. So, you know, okay, we'll set it. So if the dot product of these two vectors is greater than certain, some constant, right, in this case 0.966, because it's equal to cosine 15, right, I'm going to make can pay respect to true. So now if I run this, I should expect it. So it only shows up when I'm looking towards this text here. Does that kind of make more sense? Right now, right? Even if I'm like this far away, I can still trigger this pop-up. Where is it? Right, there you go. I'm like super far away, but I can still, you know, trigger it, right? And then in this case, right, you would have to constrain it. Okay, so well, I have this dot product, you know, condition, but you know, also make it so the distance from, you know, the camera where I am to wherever the text is, right? Magnitude, right? Make this, you know, make sure that it's less than, right, let's say like 0.7 f. Then this would only activate if I am within kind of this sphere. All right, so how do we feel about dot products? Good? Because I was thinking we just do another one of these, if that's fine. There's actually two parts to it. One of them doesn't require dot product. So if you go to C5, right, script C5, and then scene C5, right? So if I play it, you kind of get this, right? And what I was hoping is we kind of, you implement a game that me and Oscar made, a game called Hamstar. We kind of make the gameplay mechanic for that. So let me give an example, right? So this is kind of the game. It has a simple control scheme, right? If I click, if I left click, the hamster ball is gonna launch normal to the planet, right? That is, you know, orthogonal to the planet. So, right, it's gonna launch like that. If I left click right here, it's gonna go off, you know, that way. And then if I were to click, if I were to right click, then it boosts in the direction it's heading, right? Parallel to the planet. So, right, you would expect it to kind of, you know, boost clockwise. Let's say I'm going counterclockwise, right? Oops, I want to make it go counterclockwise. Okay, yeah, counterclockwise. Now it goes counterclockwise because it was moving, you know, counterclockwise direction. So that's kind of what I want you to implement. Let's go back, right? If we look at the code here, right? I'm basically saying in update, if I left click here, then I want you to launch the ball. And if I right click, I want you to boost, right? These are methods that are invoked when, you know, these if conditions are held. And the places I want you to kind of change is in the launch method and the boost method here. So the launch method is the one that doesn't require dot product. It's the one where you kind of boost the ball away from the planet. And I've kind of gave you these variables that you can work off of to make that happen. And the end goal should be to set launch force to be the right vector, which is a vector that is heading away from the planet with a length of 10. So that's what you should try to get. And then there's also the boost method here, right? And the boost method is kind of similar to the launch method, except now you're going parallel to the planet. So now in this case, you have to kind of rotate your vector, right? And I gave you kind of these quaternions to rotate your vectors 90 degrees. So do people kind of know how you would implement this? I think the launch one, right? That uses vector normalization, you know, and then scaling it up. So that one should be relatively more simple than the boost. All right, I think we have, okay, so we have 30 minutes. Okay, I'll give, I don't know, maybe 10 or 10 minutes to do this one. Tell me if you're like, just don't know how you would approach this. Although I should mention, right, I didn't know about this like until like a few days ago, right? If it makes it any easier, right, there's a quaternion that I wanted to rotate by, but there's actually a method that you can just get the perpendicular vector, right? So let's say, you know, I pass in some vector that would give me the perpendicular vector that is rotated 90 degrees in a counterclockwise direction. I don't know if you can read that. Maybe it's too small.
Oh, okay. I was like, which direction does it go?
Yeah, it goes. It says here, right, rotated 90 degrees in a counterclockwise direction.
Counterclockwise.
Yeah. So you can use this method if you want, or you can use quaternion, right? I kind of gave like use cases for it, right? Multiply quaternion by a vector, right? To go clockwise, right? If you want to go counterclockwise, use this quaternion.
While the ball is moving around the planet, it's actually always moving tangent. The velocity is always tangent to the circle, so you don't really have to do anything. You can just take the velocity and slap it in.
Well, it's not exactly right tangent to the planet, right? It can like kind of, right, in terms of like code, right? It can be like the velocity, there's a bit of deviation, right? It's not gonna be like it's not gonna be like that, right? Most likely, but it's, right, the velocity might be like this, this, right?
Okay, yeah, fair.
Does that make sense? Yeah. So you would have to check, okay, well, it's the velocity kind of, you know, on this side. The problem that, right, you could like think of it as a right dot product is either greater or equal to 0 or less than 0, right? You can kind of see it as a binary case. And the info I gave you here is, right, let's not put this directly on top. Info I gave is the ball position and the planet position. Right? One thing you can do, right, if you've done the launch method, is, you know, get this vector, right? And you also have the velocity. Let's say it's kind of going like that. Let's, you know, just for no reason, take the dot product of this, right? What you would end up is getting, you know, dot product of 0, right? Because, you know, they seem to be kind of orthogonal.
Close to 0.
But it would also be, you know, the same if it was going in this direction. And let's say if I had a velocity kind of go in this direction, right? This would give me the same dot product as if I, you know, had a velocity in that direction. So, you know, something's not really working out. I was hoping I could kind of abuse this property, but it doesn't seem to be working out. That is because, right, when we're taking the dot product of this and these velocity vectors, the velocity vectors need to point downwards for it to change sign. So what if we rotated this difference vector here to kind of be like this? Now we have this line to make it, right, to make this side positive and then this side negative. Does that kind of make sense? So now if the velocity is facing in this direction, right, that is take the dot product of this vector that's been rotated, this different vector that's been rotated by 90 degrees clockwise, and then take the dot product of the velocity. If we see that that is positive, then it's going, this way. Otherwise, if the dot product is negative, then it's kind of going this way. I think just rotate it 90 degrees, right? Get the difference vector, rotate it 90 degrees, and then kind of just try something with it. Maybe I guess I should I don't know, re-emphasize, right? The dot product calculates how similar, right, these two vectors are in terms of the direction they're facing. I'll go over the solution, and then we'll do cross product real fast, and then I'll do the cross product thing as well. Okay, so launch, right? Left click, thing shoots off normal to the planet, right? Orthogonal to the planet. So what we would do is we kind of want to, let's say we have the planet here, and then we have the ball here. We want to get this vector, which we can get just by, getting that different vector, right? So let's do that first. Make it so launch force equals, right, ball position minus planet position, right, from the planet to the ball. Right, of course now we want to, right, we want to launch it at a certain force, right? In this case, we want the vector of 10, length 10. So what we want to do is normalize this and then multiply it by 10, right? I also added a constant float. I didn't mention this, so right, I was expecting you multiply it by whatever the launch force magnitude is. And then if we go back, we would get this effect where if I left click, it jumps up away from the planet. Right. Now for boost. We do the same thing, but like I said, we want to rotate that vector to be kind of going in the tangent direction. So we have, let's see, I'll just call this to be the reference vector. And then we get the ball position minus the planet position, right? And then we want to do the same thing where, well, we don't have to normalize it yet, right? But I do want to rotate this. So I might do something like, okay, well, get the counterclockwise version of this, which we can do by rotating it by a quaternion, right? I gave some examples here. Another thing you could have done is just use the vector to perpendicular method, right? So now we have the vector orthogonal, and then if we were to take the dot product of that, it would give me whether I'm kind of on, quote unquote, on the right side or the left side of the planet, right? For the velocity vector. So let's say, okay, well, let's take the dot product of that reference vector that's now clockwise and the ball's velocity, right? And we want to check if this is greater than 0. That means I am going kind of in the same direction as that reference vector, right? Let's say, okay, well, if this is true, if it is going kind of, in that same direction, which would, if the ball was on top of the planet, it would be, going in the right direction. Okay, well, go boost in that direction. So we would do, we would set boost force to be it would be that rotated vector, right? We normalize it, and then we multiply it by whatever length I said to be. In this case, it's 4. I also have this float thing here, which I set it to 4 as well. So boost force mag, right? That's for the right direction. Otherwise, right, my velocity vector is on the other side, right, the negative side. So I would make it so I would go in the other direction. So if I were to go and then now, you know, start right clicking, I should, you know, start boosting in that direction. Did those examples, I don't know, did me going through that kind of make more sense? About the same? All right, 625, all right. I'll quickly go over cross product, right? I do not want to go over time, right? I don't want to keep you all hostage, so. All right, let's quickly do cross product. So cross product does not exist in 2D. It only exists in 3D and then 7D for some reason. So it would look something like this. Okay, so you have two vectors, u and v, and you want to cross them. It has some like really weird definition where it has like, okay, well, multiply it by, you know, uy and then the vz minus uz vy. I'm not going to go over that, right? It's weird. The point is, the cross product of two vectors in three-dimensional space, let's say, I don't know, that's like x, y, z. Well, let's work in unit coordinates. That's y and that's z, right? So let's say we have two vectors like this. What you would get is the vector orthogonal to both that vector and that vector, right? So very useful, right? Let's say you have like, I don't know, some kind of mesh here, right? I don't know, like a pyramid. You can get the normal of that, of this mesh just by, you know, getting, let's say you have vertices. You can get this difference vector, and then you just cross those two together. Another use for it is kind of orienting or like getting the correct orientation of an object on like a slanted slope. So let's say, how would you draw this? Right? If there's a camera here, right, and it's kind of like looking down like that. Let's say it's like this. Right? I want certain object, right? I want to place down an object, but I want to place it so, you know, the top is, you know, I can draw it better. The top is kind of, you know, facing in that orthogonal direction, as well as the forward vector is kind of, you know, in the same plane as, you know, the direction that the camera is facing. And you would achieve this by using the cross product twice, which I may show depending on how much time we have. Another thing to note, right? Honestly, the orthogonality property is kind of the most more powerful, you know, like that's all you really need to know. But another thing is, right, the magnitude of this, right? This is going to equal to the area made by those two vectors, right? I don't think, I mean, unless you're like computing like some volume, right? I don't know if that's too useful, but you know, that's good to know. Another good thing to know is that U cross V is not equal to V cross U, right? The dot product, right? You can do that. U dot V is equal to V dot U. In this case, right, it's not equal, but it is the case right, the negative version of it is equal to u cross v, right? They're anti-commutative. So how do you know, like, which order to, apply this operation, right? And there's this thing called right-hand rule, left-hand rule. So in Unity, there's this notion of left-handed coordinate system and right-handed coordinate system. Unity uses a left-handed coordinate system. Okay, let's look this up. Left-handed versus right-handed coordinate system. Let's see if it shows up. Right. So it's gonna be like, okay, well, in both left-handed and right-handed, right, the y is pointing up, but it could be that the x comes first and then the z, or the z come first and the x, right? Unity happens to be left-handed, right, in here, right? Unity 3D is left-handed, so you have to use the left-hand rule for calculating the cross product. And the way you would do it is, okay, let's say you have the thumb, the index finger, and the middle finger, right? And I don't know, you have these two other fingers here, right? This would be U, this would be V, and then this would be the cross product, right? So you have to make sure, okay, well, if I want to get, if I have two vectors like this, and I want to get a vector kind of going upwards like that, I have to first, do the cross product of, whatever one is more in front, and then do the V, right, to get that. Otherwise, if you do V cross U, you're going to get a vector that goes down like that. Make sense? Okay. Right, 6:31. I'll go like, okay, 3 more minutes, right? I'm just going to speed through checkpoint 6. What I was hoping we could do is make it so, right, kind of like in Half-Life or Portal, right, you can pick, like, turrets up and then stuff like that, right? It's kind of like, that's kind of like what's happening. I picked up something and it's kind of in front of my camera. And I was hoping, right, if you kind of put it down on a slanted surface, it would orient itself correctly. So let's see how we would do that, right? Go to exercise scripts. Like I said, for orientation thing, I said, like, okay, well, you could do something with performing cross product twice. So what we want to do is kind of get, okay, well, I want to get whatever my side vector would be. Okay, I'm facing in this direction. What is the vector kind of like going outwards to the side? So I can get that by using the cross method, and then using, the left hand rule. I could do something like, okay, well, I want to get right, the camera direction, and then I want to cross that with the normal, and that would get me the vector that kind of goes to the side, right? And then you can even kind of draw this, right? Debug.draw line wherever the hit point is. Okay, I want to draw side. So now, if we place it down, now we get a kind of a vector going, sideways, right? Now what we want to be able to do is kind of get a vector going forward, and that's just the cross product of whatever that side vector is with, the normal. So what you would end up doing is, let's see, okay. You would do, now you would set whatever the forward vector is to the cross product of the side and the normal, right, which I've set up here. And then if I do this, oh, okay, I did it in the wrong direction. This is what happens if you do it in the wrong direction, right? It points in the other way. So to get it looking the other way, I would just swap these around, right? And then now you would have it, so now it's kind of like facing kind of in the right direction. Does that, kind of make sense? Now right now, it's not like really looking in the right direction. Like you can see it's like kind of like looking to the right, right? And one thing you could do is like, okay, well I could get the up vector, up vec, which is the up vector of the camera, and then I would do, instead of camera direction, I would do up vec, and then side with normal. So now no matter where I look, it's kind of looking in the same direction. I kind of went through the cross product part, but hopefully you can see like, okay, it has its uses, right? Now like I can go around, no matter which kind of surface I look at, it's kind of orientating itself in the correct direction. So yeah, I mean, that was it. I guess, right, we went through a lot of things here, right? Vector addition, multiplication, dot product.
Thank you, Brian.
Is that kind of exhausting? I feel like everyone's going on.